Alright, Federal Railroad Administration, Office of Railroad Safety Track Inspector Rail Defects Reference Manual. Section 8, Rolling Contact Fatigue. Alright, rolling contact fatigue is RCF, conditions develop in railways and wheel-rail interface in the most railroad systems. Any type of surface condition can be an influential obstacle in detection of an underlying real defect. In the doubt and uncertainty integrity of the test process, identify the detector car operator concerned surface conditions. The option to record rail sections invalid tests report the location of the railroad detailed below at some of the more critical types of surface conditions we encounter. All right, shells are identified progressive horizontal separation, generally the gauge side of the rail, which may crack on out of any level, usually an upper gauge corner. Shelling may turn down in transverse separation when detected. Classified detailed fracture, uncapped, gutted shells will result in dislodgement of parent metal in the rail section. This is figure 48. It shows the gauge side shelling showing the severe parent metal decay. Flaking originates surfacing rail, the commonly found with near stock rail and or switched concentrated load cold water steel. Flaking can be identified with the railhead surface horizontally separation, scaling, chipping of small segments of parental rail. This shows figure 49 shows a centralized flaking condition showing chipping of the parent metal. The burned rail. A burned rail is a railhead condition that results in friction, slippery locomotive drivers, the damaged area, gradually chipping the roughing of under the repeating traffic. Potentially transverse defects develop in the thermal cracks associated with the burned area. Once the surface condition reaches the critical stage of the displacement of the railhead surface material, the detection of the underlying rail flaw is obstructed. Figure 50 shows the thermal crack of a burned stock rail. The head checking. Head checking is identified by site operation metal gauge and railhead, normally found in the high side of the curves. It's also common in the switch areas due to the lateral force induced by the railhead with the wheel displacement throughout the turnouts. Head checking of the turn down develop into the transverse separation. See the gauge side checking and flaking. Spalling. Spalling is generally referred to as the displacement of the parental metal for the railhead from the high contact stress associated with silica loading. This will also be referred to as slight flaking, minimal stage severity. Further deterioration of the railhead can increase the amount of metal displacement, resulting in significant spalling condition. Figure 55.2 shows a flattened railhead showing the displacement of parent metal spalling. Note that it is responsible for the rail defector car operators to properly identify the types of the railhead surface conditions that can result in properly invalid tests of the rail section in which the condition is contained. Extra care should be taken with in the interlocking areas. The operator should also be aware of other conditions that can result in invalid tests. Effects of rail wear. Severe head wear distortion can alert the normal angle refraction of ultrasonic beams from the transducer to the critical level. The ultrasonic signal do not penetrate in the accepted angle or to expected location in the specimen, therefore is probably reflected. The sound beams normally associated with the internal rail flaws may be identified with the testing system with a defective portion of the rail section. In effect, with the severity of the head wear characteristics significant, it can impact the integrity of the test. Rail flawed development and failure. Non-destructive test systems are designed to perform optionally on the testing specimen. Unfortunately, much of the rail is heavy haul industry affected with the loading stress. The result is much of the plastic deformation of characteristics of the rail specimen that were previously described. These conditions impact the development of the rail flaws. The conditions also impact the technologies currently used in flaw detection, limited the detection capabilities. Therefore, it is important that emerging technology developments continue in the effort to evaluate the impact of adverse testing specimen conditions. Normal railway maintenance, such as lubrication, rail profile maintenance, and track maintenance programs, all greatly increase the life cycle of the rail. This practice also deterrents the crack growth life, internal rail flaws. Without aggressive track maintenance programs, rail flaws, development flaws will continue to be eschewed, result in service disruption in heavy hauled railways. Section 9, Rail Welding.